tube whose ends I marked orange and black. I'm afraid these are colors of Princeton University, not Harvard. And I'm going to set its spin by launching it. And you'll see that it spins around the middle, so I'm already trying to misguide you. There is no reason why we should see one end better than the other end. Now, let me launch. Do you see that? That's curious. Which color do you see? I see black, don't you? So that's strange. Maybe we see black because black is darker than orange, so we see it better. But if I shake it, I see orange. I can do it with my left hand too, and it's still orange. That's very curious. So mystery number one is, when do I see black and when do I see orange? Well, in fact, I've already told you, when I shake. Also, when I rub it against my hand, it's black again. So that's the first mystery. But there's a mystery number two, which is, how many spots do you see? I see 4. Why 4? It's not as if I'm launching it with any care. I casually launch it, and it seems to be always 4. In order to understand this better, I brought another tube, similarly marked. And this time, you have to wait a little bit until it settles down. How many do you see? 3. And I'm going to make it orange. 3 again. So what is 4 about this, and what is 3 about this? You are probably guessing already. What we see is that the first long tube, whose length to the diameter ratio is 4:1, shows you 4 spots. And the second one, 3:1, shows you 3. Now we can guess what 2:1 will show you, and 5:1 will show you, and so forth. But first, the 0th order approximation, as we like to say. The way we are launching, as you might have seen, is that I'm pinching one end down, and then it pops out. Okay. When I pinch it down, let's get some terms in order to clarify the issue. This is going to go into a certain motion, which is a combination of this kind of spin, which we shall call revolution, and also spin around this axis, and which we shall call rotation. So revolution like this, and rotation around this axis. Now, when I launch it, it's going to, for example, let's look at the point which is at the other end of the tube. That end is going to advance like this because of the revolution. But at the same time, look, I'm pinching it down. So at this end, there'll be a forward spin, top spin, which adds to that velocity. So that end is going to be moving quite fast. Revolution plus rotation. At this end, on the other hand, it's going to move forward because of revolution again. But at that end, we have a backspin, which subtracts from the revolution minus rotation. So this end is going to be moving slowly. And the fact of the matter is that the end we see, the spot that we see, is the spot that is moving slower and not faster. Okay, that's plausible, but it's not so satisfactory. I mean, why should we see something slow better than something fast? Maybe human eyes have a good frequency to capture a certain velocity, and maybe they're happier with fast things. So let's try to understand a little better. Experiment, please. When I launch, initially, because I'm launching very carelessly, it's going to start sliding. And we have seen, however, that if I press down on the black end, we see black, and if I press down on the orange end, we see orange. So far, we understood, but as I said, on the plausible level. This explanation so far doesn't at all explain why 4, why 3. So let's come to grips with this. When I launch, it turns out it's starting to slide, but soon it's going to go into rolling. And while it rolls, it's doing this. Let me exaggerate the motion. That. It's rolling, 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 rolling like this. Okay? Rolling like that. Now, in the course of this rolling, please, in your imagination, place from above a transparent ceiling so that it touches the tube, this tilted tube, just so from above. There's an up and down symmetry of the motion with respect to the floor and the ceiling. If it's rolling on the floor, it means that it's also rolling under the ceiling. It's this tube, while going around in a tilted fashion, is rolling under this imaginary ceiling that we put from above. This slide, please. Now, that blue spot, which unfortunately with this laser pointer becomes green, is the mark that I left either orange or black on the tube. What kind of trajectory is it going to draw when the tube rolls under the ceiling? It turns out that that trajectory is this kind of hanging chain pattern called cycloid. It has been studied extensively by mathematicians and physicists for many centuries. And just as you imagine driving a car along this kind of funny road, and then there's a cusp, and you have to go into this cusp and back out. Well, how can you do this? You have to stop there, don't you? You cannot keep going, however slowly. You have to stop there instantaneously and then back out immediately. So at those cusps, each time the spot comes, it has no choice but to stop instantaneously. Puff, and then start going again. So as the thing rolls round, the spot above is describing this kind of cycloidal trajectory and going puff, 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 puff. Each time it shows up its face towards us, who are looking down from above, it stops. And that's why we see those spots so clearly. And how many times is it going to have a cycloid around this trajectory? Well, it has to do with the ratio of this circumference of the circle that it's describing and the disk which is rolling, cross-sectional disk of the tube which is rolling around. You see, as it rolls, 1, 2, 3, 4, and so on. But that ratio is exactly a ratio of the diameter of this circle to the diameter of this circle, which, roughly speaking, because this angle is small, is the ratio of this length to this diameter. And presto, that's what 4:1 and 3:1 is. So I was very happy to see this, but I hope you are too. But when I found this phenomenon, as I say, I didn't understand what was going on. So I cut a plastic tube into integer ratios, whole numbers, 4:1, 3:1, and so forth, and then started understanding this. I now regret not having cut a tube in non-integer ratios. For example, if the ratio of the length to the diameter were, say, 4.1 to 1, a little more than 4, then you can guess, I can guess what's going to happen. You'll see 4 spots, but they'll be sort of slowly going backwards. It's called a precession, retrograde precession, shifting in time. If it were 3.9 to 1, a little less than 4, then it will be a prograde precession. Those 4 points will be going slightly forward and so on. But what if it were 3.5 to 1? It will be exactly between 3 and 4, and the thing will not know how many to show. I'd love to force nature to show us what it does. Unfortunately, so one of my ambitions while I'm spending a year in Boston is to be able to cut the plastic tube into non-integer ratios. If somebody can help me. Thank you very much. Okay. Now, this kind of motion, it turns out, is extremely important in a whole range of applied mathematics, applications of mathematics. There are 2 spins involved, as we saw, rotation and revolution. Now, what kind of mathematical pattern gets extracted from this motion, this dynamics? Well, if you have one spin which is going, at the same time, you are combining another motion. Let's say, for simplicity, in the first instance, that the combined motion is a straight line motion. You can think of a circular motion which is being blown, swept away by a wind blowing. Then you can see what's going to happen. You're going to get a spiral kind of pattern, right? You can see. But here we have 2 spins combining. So this wind itself is going to be a revolving wind. So what's going to happen? Well, you get a spiral pattern, but which is spiraling and winding around on this shape, which has been traditionally called a torus, the surface of an American donut. I'm now careful to say American donut because I've visited countries where the donut doesn't look like this, unfortunately. But anyway, so it's on a torus. And miracle of miracles, it was discovered towards the end of the 19th century, beginning of the 20th century, that in a specific sense that can be technically defined, all dynamical problems that you can encounter naturally in nature, which can be solved exactly. Again, you have to define what solved exactly means, but solved exactly can be expressed in terms of a picture like this, and they all spiral on what is called an invariant torus, or invariant tori, and that is the vision that was developed by Henri Poincaré, a French gentleman depicted here. Okay, so that's the case when you can have exact integrability or exact solvability. But let's see what happens when the problem is no longer so pure and is subjected instead to all kinds of perturbative influences from the outside world, messing things up. Then what? Sometimes you run into people who happen to be walking around with an inclined plane, and here are two espresso cups. And which one do you think is more stable if I try to balance them on my finger like this? I'm not sure that I can balance either of them on my finger, but this is fairly stable, yeah. But this is extremely difficult to balance, as you can imagine. Okay, so this pinched one, concave one, seems to be more stable than this bulged one, convex one. But now, let's try to roll them down the slope. First, the seemingly unstable one. Can you make it roll down the slope? Yes, it rolls down all the way down the slope. It wobbles a little bit, but no problem. Let's make this roll down the slope. Now, I have to be very careful, like this. Oops, no, it sort of shot off in the end. No, it goes off a little bit. I try to do this here. No, it goes off. Not quite doing this. Oops, no, it goes off. No, it went off. We don't manage. Whereas this one, I don't even have to watch what I'm doing. It just goes down the slope. So this motion is stable, and this motion, in a certain sense that you have just witnessed, is unstable. And you can try afterwards to try to make it go down the slope. It's extremely difficult. Huh? It's not going to. And so what? Oh, I managed that. So what is going on? What's going on is a very universal mechanism, it turns out. Slide, please. That's the convex or the bulgy one. And let's say that because I'm somewhat clumsy, and also, of course, nothing in nature happens exactly, yeah? Idealization accepted, you cannot place this exactly in the middle of the rail. So it's going to be a little off the middle. Then what's going to happen? You can see that this bit of the espresso cup, which is touching, is going to be touching the rail, left rail, along a large circle. Do you see that? Here, it's going to be touching the rail along a small circle as it rolls. So effectively, you have wheels, large circle here and small circle here, large on the left and small on the right. And what kind of motion is it going to produce? Well, it's going to naturally turn this way towards right. But rightward motion is exactly the motion that would correct this initial deviation, which was to the left. So there is an automatic recall, so to speak, or correction, and that mechanism is what is called stable. We often talk in daily language about something is stable and that personality is unstable and so on. But what do we mean exactly? Well, this is what it means for stability. It means that whatever small perturbations you introduce, there's an automatic self-correcting mechanism that brings you back to the balanced neutral equilibrium state. In contrast, if you have this concave one, which is pinched in the middle, well, let's say that it's deviated a little bit to the left. What's going to happen? Well, it's touching the left rail along a small circle, but the right rail along the long circle. So this big circle, this small circle, form wheels, and how will they roll? They are going to roll off to the left. But the left is already the direction of the deviation. So what's going to happen is a runaway effect. It tends, given a small initial perturbation, which is always inevitable, to exaggerate that deviation and make it worse and worse and worse and worse. And that is the self-exaggeration which is called unstable, and that's what we should mean. So here we have very nicely illustrated a mechanism for stability and a mechanism for instability. And that was what was happening when you take into account some perturbations from the outside world. Well, that study or that investigation was about a single object, those espresso cups, single espresso cups rolling down the slope. Let's stretch the model further and see how it breaks by now looking at lots and lots of bodies interacting among themselves. A huge population. Well, not so huge. Experiment, please. I brought here a box which says on the cover, I don't know if you can read, Chai Gruzinski extra Georgian tea in Russian. And if you open it, it says, Как заваривать чай, how to brew a good cup of tea. Very scientific detail and so on. But that has nothing to do with the experiment. Inside, I'm carrying cedar balls. And one of the things that you can say about this experiment is that it smells nice. I mean, how many other experiments can you say that about? Anyway, so here is a soup bowl that I borrowed from a cafeteria in Cambridge. And if I put 2 or 3 balls and swirl this soup bowl, you see that those cedar balls, those balls, circulate in the same direction that I'm swirling. By the way, because we are among grown-ups here, when I say swirl, I mean I'm doing this. I'm not rotating like this. Yeah? I'm keeping this parallel to itself, but doing that. That's swirl. Anyway, so I swirl, and expectedly and rather boringly, those balls circulate in the same direction that I'm swirling. But now, let's increase the number of balls. And when I swirl, you see that they start circulating in the opposite direction. Huh? I'm swirling like this, but they circulate in this direction. Do you see that? So there was a transition. We saw that when you have 1, of course, it goes in the same direction. In 2, 3, that was the initial experiment. But with 4 already, there's a lot of hesitation. They're still going in the right direction. But with 5, there's so much hesitation that it's not clear which way you're going. And 6, there's a nascent beginning tendency to go backwards. And 7, it's quite clear already that they're going backward. It's like the transition from gas to liquid, it turns out. And this kind of thing is called a phase transition in physics. Phase transition refers to gas to liquid, for example, condensation, or liquid gas evaporation, or liquid to solid, freezing, solid to liquid that's melting. So ice, water, vapor. I had to practice a lot in order to say this without making mistakes. But anyway, so that's what's happening. And in order to show you that it is a phase transition of freeze and salt, if I keep increasing the numbers, then they freeze solid. Well, okay. So that's quite interesting. And what's happening is that when you have few of them, these balls are effectively acting independently of one another. And they're being bounced off the wall of the soup bowl, which are coming to hit them. And so, of course, they go in the same direction. But when they start getting crowded, when they have to take into account the neighbors, lots of them are now crowding one another, then they start rubbing against one another. And whatever input of momentum or hitting from the wall that comes in is dissipated, scattered in random directions among the neighbors. On the contrary, if your neighbor is rubbing you this way, then you have to rotate the other way. So you are being controlled by your neighbors as to, especially by the wall, as to which way you are rotating. And that transition from the, if you like, the impulse-dominated dynamics to rotation-dominated dynamics, from linear momentum to angular momentum, is what the transition is all about. Okay, so this is probably one of the simplest examples of phase transition. Can you have the slide, please? And that's what happens when you have a lot of numbers of things interacting among one another. Okay, phase transitions, the phrase that I pronounced before look like this, which probably are familiar to all of us who have lived in this universe for a while. Okay, that was when we increased the number of agents or players. That was one way to break our model and make it do things that were surprising. Let's stretch our model then in another direction. we said that those strange rotations that end up making you go backwards with respect to swirling have to do with mutual rubbings among neighbors. That has to do with friction. Let's see what happens if you start getting rid of the friction, make the friction smaller and smaller and smaller. That's quite interesting. In the limit, as you take the limit of friction becoming closer and closer to zero, what do we expect? Well, we expect, don't we, that in the limit we recover the behavior when there is no friction whatsoever, zero friction. So that kind of thing we would like to study. And the best way to, I think, start looking at the situation is through photographs. Here we have a photograph. It's an experimental photograph, not computer generated, of some obstacle and the fluid, water, for example, which is flowing past it from left to right. All those photographs, fluid is going from left to right. And there is a parameter that fluid mechanicians like to use, because when we say, well, friction, large, small, but large or small with respect to what? You know, for example, you have much more money than I do, but I have much more money than my pet frog has. So, I mean, large or small, you have to have a scale. And this combination of density times size times speed divided by viscosity, that's the technical term for friction in a fluid, turns out to be a good measure of large or small. It's an absolute number, pure number, dimensionless number called Reynolds number. Now, but for the purposes of this discussion, just fixed density, size, and speed, ignore all of that, and think of viscosity only. So if you have a lot of friction, Reynolds number is small, for example here, that's a lot of friction, and as we start decreasing the friction, Reynolds number is going to become higher and higher, okay? So from one picture to the next, we're going to decrease the friction, make things smoother and smoother, okay? Well, so that's what it looks like when there's a lot of friction. Everyone has to behave sort of goose step to the same tune. So it's very nice. And this kind of flow is called laminar. Laminar in Latin means thin slice or layer. So everything is organized into thin slices and layers. If you decrease the viscosity, in other words, make it a little more less frictional, then what's interesting is that behind this obstacle, you see the birth of vortices, those whirls. Interesting, and that's when Reynolds number is about 10. So I have, in this measure, decreased the friction by a factor of 100. And then what happens if I decrease the friction by a further factor of 100? Here we had two vortices behind that are being born, and what happens is this. Fluid is coming from left to right, and behind this obstacle, you see this fantastic pattern of what is called the Kalman vortex street. This picture, I think, is one of the most beautiful photographs, artistically speaking, that have ever been taken in the history of science, and it was taken by a Japanese experimentalist who passed away about 3 years ago, Tadashi Tokieda. We tend to underestimate the contribution of experimentalists and technicians who do this kind of work, and I think Tadashi Tokieda should be remembered together with this photograph. It's reproduced in all textbooks of fluid mechanics and lots of good textbooks of physics. Beautiful. Now, this Kalman vortex street, Wirbelstraße, can be found on all scales, it turns out. So this is Reynolds number about 100, and look at this. This is a whole carpet, if you like, of clouds streaming past, but there's a peak of a mountain sticking just above the cloud, and that sort of splits the clouds, and then behind that is this pattern, and that's the Kalman vortex street. This was taken in April last year above Greenland, an aerial photograph. So you can say that this is a giant toy for us of a Kalman vortex street. Now, going back to the, this transition, if you decrease the friction by a further factor of 10, so from that picture, further factor of 100, then you get this mess called turbulence. You can see that the nicely organized vortex street has now degenerated into this huge mess, not chaos behind this obstacle. And as you lower the viscosity, friction, more and more mess develops in the wake of this body. So what do we think happens if we bring the viscosity all the way down to 0? In other words, when you take the limit Well, we should have a massive maximum mass, turbulence, right? What happens is this. At zero velocity, it looks exactly the same as this. Again, laminar. So here we have a discontinuous behavior of nature. You keep sort of persuading nature to do a little more, a little more, a little more, a little more, but in the limit, at the extreme limit, boom, nature behaves completely differently from what it has been doing until then, and you are faced with this discontinuity. Here's a toy that shows that discontinuous limit. Experiment, please. And this was made by my friend Andy Ruina of Cornell University. Now, those two heptagons, 7 gons, are made of metal, and they have, I can assure you, exactly the same mass. And also, the mass distribution inside each is completely homogeneous. That's a complicated way of saying there's nothing hidden. I mean, there's no sort of empty chamber inside, or there's no sort of concentration of mass on the edge here, and so forth. What you see is what you get, and quite heavy, in fact. So, but of course, there's something that I'm not telling you is true, but I can assure you that they have the same mass, and mass distributions are completely homogeneous. However, there's a difference between those two. Let's try to make them roll. This one, when I try to make it roll, it rolls willingly. How about the other one? No, it's very reluctant, and in fact, it refuses to roll altogether. And when you superpose them on top of each other, you cannot possibly see the difference. I hope you can't. I can't. Huh? Eric, can you? Thank you very much. Oh, that's good. That's good. Good. So thank you very much. I should buy him a cup of coffee afterwards. So you can tell the difference. So what on earth is different? What is different? Well, the mass, no. I said that the masses were the same. Well, maybe there's more weight on the outside on one and more weight in the same. No. I said the mass distribution is the same. What I didn't say is that the shapes are the same. The shapes are not quite the same, although you cannot tell the difference. The difference is that the one that rolls, this one, is not actually a heptagon. It's a heptagon where each edge has been bulged out ever so slightly outward. Yeah. And the one that does not roll is a heptagon, but it's not quite a heptagon. It's been pushed in each edge ever so slightly inward. So, the slides, please. In the one that rolls, that's the picture. You see, as you go from one vertex to the one corner of the heptagon to the next heptagon, the point of contact can actually move smoothly, continuously along the edge. You see, it sort of rolls over, and the center of rolling actually transits from one corner to the next smoothly. But that's because this is slightly bulging out. What if you have the other case where it's straight or slightly bulging in? Then there is no contact as this whole thing rolls. So while it's rolling, all of this edge is in levitation. And it's going to be until this next corner bangs on the surface. And that bang shock is going to lose all the energy and stop the motion. Yeah. So that's the difference. Slight bulge out, slight squeeze in. But in absolute value, that difference is only 0.1 millimeter. Do you speak in metric? That's tiny anyway. And because the diameter of this thing is about 10 centimeters, it's 1 in 1,000. It's 0.1%. In other words, if you are paying with, say, a $10 bill, you are arguing over a change of 1 cent. But that tiny difference, and theoretically, any tiny difference whatsoever, provided it's not zero, is going to cause this massive qualitative difference in behavior. And so, in particular, if you start from epsilon, a very small number, and keep observing the behavior as epsilon becomes smaller and smaller, for every positive epsilon, you'll see a smooth rolling. But as soon as, and exactly when epsilon becomes zero, boom, the behavior changes qualitatively, a discontinuity in the behavior of nature. since we're talking about heptagons, let me have a little digression and make a little digression and show you something nice. I brought a strip of paper, and do you know how to draw with ruler and compass, say an equilateral triangle, square, and things like that? Well, maybe some of us remember, some of us learned it recently, but it's not so easy. But I'd like to show you a very, very nice and foolproof way of making a regular pentagon that is 5-gon, 5 corners, 5 edges. You take a strip of paper, and you make the simplest knot that you can think of, which in my case is this one. Having made that knot, you tighten that knot, and as you tighten that knot, you flatten it, and as you tighten it, you flatten it, and then you negotiate, coax it, and tighten it, flatten it, okay? You make that knot tighter and tighter, and then as I do that, I flatten the knot at the same time, and then in the end, when you finish, what you got is this shape. And in order to show you what we have obtained, let's get rid of the extraneous bits that are sticking out. What we have gotten is a regular pentagon. I didn't have to think, I didn't have to be careful, where I had to be a little careful. All I had to do was to tighten the knot, make a knot, and then tighten it and flatten it. If you have been to Japan and stayed in a traditional inn, they lend you a nice pajama called yukata. And there's a belt, long cloth belt, very soft cloth belt that they lend you also. And usually, traditional way to present this belt is to fold it in that pentagon pattern. And that's where we learn it from. And here, in order to make this pentagon automatically, you see, I'm not intelligent, but nature is. And I happen to know how intelligent nature is. In order to make this, we started with a knot that had one pass, if you see what I mean. Passed it once. It turns out that if you do 2 passes, you get a 7-gon. 3 passes, 9-gon. 4 passes, 11-gon. And this is what I made, a regular 11-gon, which is not supposed to be constructible with the ruler and compass according to some theorem in geometry. Let me show you a little close up. That's an 11-gon. Okay. All you have to do is to tie strips of knots and then flatten and tighten them. You might have noticed that 3 was missing in this sequence, 5, 7, 9, 11. So what about 3? Well, in order to make a 3-gon, that's an equilateral triangle, you have to make a knot with 0 pass. And that's depicted there. Curious. Okay, so that was, after this digression, what happens when you take the limit of smaller and smaller friction, or one of the friction becomes larger and larger. Now, in some sense, that's messing with a law of nature. In other words, we have not the law of nature, but the parameter of nature. We have one parameter called viscosity or friction, and then we try to look at situations where the viscosity changed. But let's be more ambitious. Let's stretch our model and do something that is, in a sense, more dramatic. Keep the same situation, and can we produce a phenomenon where something goes up and up and up and up and up and up and through the roof? Mathematicians like to talk about divergence to infinity. Something explodes in finite time. I'd like to show you such an example. Experiment, please. Have you ever witnessed a coin dropping? You hear this typical shuddering sound. It's so typical that, in fact, if you are in a bar or restaurant and if you hear this, you think, so somebody dropped the coin. Well, the coin that I brought here today is an exaggerated coin. Yeah. If that was a quarter, this must be very, very expensive. And, yeah. And because it's large and heavy, it's made of single metal, and you can imagine the trouble I had passing this through the airport securities. But anyway, and because it's heavy, the motion lasts for a long time, and because it lasts for a long time, you can see many phenomena that escape our attention. Mind you, it's going entirely on its own. There's no motor underneath, and there's no magnet. I'm not sort of with telepathy, which I'm, of course, capable of, driving this from the outside. It's just going and going on its own. And as it goes, you can hear that something is getting accelerated, going faster, faster. But that's strange because the rotation is not getting any faster. Rotation is quite steady, but something else is getting faster and faster. It's some sort of flapping motion. It's lasting longer than I thought. And it's going faster and faster. Now, sooner or later, it's going to finish. And when it does, I would like to invite you to watch it, but also especially to listen to the sound that it makes, gasps towards the end. Huh? Very interesting. So the sound started suddenly going up and went through the roof. A finite time singularity divergence to infinity with some idealization. You might ask, what's going on? Well, there were some theories, maybe 10 years ago or so, which said that all this effect is due to the air trapped underneath the disk. I was a postdoc in the emotional and the financial sense in Montreal, and I had already, in fact, worked out the mathematics and dynamics of this kind of thing, so I wanted to do an experiment. Well, there were experimentalists from, I think, Berkeley in California who wrote in saying that, oh, that's nonsense, this theory is nonsense, because we did the same experiment in a vacuum chamber, and we saw exactly the same phenomenon. Of course, you cannot hear the sound because it's vacuum, but you see the sort of acceleration of this flapping motion. Now, as it was correctly pointed out, actually, it's very difficult to get rid of the friction or the viscosity of air. As you make the density of the air drop, lower and lower it, and come closer and closer to absolute vacuum, the friction of the air, the viscosity is pretty much constant, it turns out. And it was known to Maxwell. So you had better have a pretty damn good vacuum chamber in order to see the effect of getting rid of the air. So that's expensive, and the poor postdoc cannot do this. So I went to a lady's accessory shop and bought this, a bracelet. Here, there is no question of air trapped underneath the disk because there's no disk. It's just a pure rim. By the way, when I went to a shop and started spinning one bracelet after another to see which one works best, a very charming shop assistant came over and said, "Can I help you, sir?" Well, you can. So what's going to happen is this. Let's see if I can do this. I'm going to try to, sorry, I haven't done this in public for a while. Okay, so I spun it from a vertical position. It's like a ballerina spinning and spinning. It's very beautiful. And that's sort of the first phase of the dynamics. But soon, you'll see that ballerina becomes tired and will go transit to a second phase suddenly, which is a different picture. Now, okay, in this second phase, it's exactly the same motion as we saw with the disk or the coin. It's lighter, so it's not going to last for a long time, but it's exactly the same physics, as you can see. So the air trapped underneath the disk has nothing to do with this. By the way, I can do this on the table as well. So, what's up then, if it's not the air? Well, it turns out that it's very important for the disk to keep losing energy because that's what is flattening it, making it closer and closer to the ground, and that's, in turn, what's accelerating this flapping. So it turns out that the crux of the matter is to see what is losing energy. And what's losing energy is, in fact, the vibration. In order to show you this, I'm not sure that I can do this. I'm going to shine this laser pointer on the surface of the mirror. And do you see the reflection there? Somewhere on the, and do you see that it's wiggling? That's the support of this mirror wiggling because this coin is doing this motion. Oops, sorry, maybe I should do it. Do you see that above the ceiling? Yeah, it's dancing. It's not because of my hand, which is also shaking. And that vibration is taking away this vibrational energy, phonons, wave of vibration, which is losing the energy. In order to convince you of this, let's repeat the same experiment on a good absorber of vibrational energy, such as a human body. You know, your human body, especially my body, has been designed to withstand all sorts of shocks. And watch how long the motion will last if I do it on a human body, a mirror supported by a human body. The entire energy quickly dissipated and ran away through my body to the ground. So it turns out that what's losing the energy is the phonons, and this is the key to understanding this funny coin motion. Let's make it go, but this time I'm going to shine the laser pointer on the surface of the coin, and somewhere up there you'll see the reflection. You can't see it yet because it's... I'm going to... Do you see that? And now, in addition to the sound, you can see also how fast it's going to keep going. And as it settles, that circle is going to become smaller and smaller. Slide, please. So, singularity, something goes through the roof within finite time. We have seen quite a few toys. We saw stability to instability transition. That's when you took the time to be infinity. And from instability, we came to phase transition. That's when you increase the number of agents or players. And then we took also the case of when the friction became very, very small and became zero effectively. And we witnessed this amazing instance of discontinuous limit and singularity in finite time. That's the singing and shattering disk and more. All of these things made us travel through quite a lot of science. Invariant torus, integrability, non-integrability, stability, instability, asymptotic behavior, phase transition, discontinuous limit, structural robustness, and so on. Now, where do those this wonderful ecology, if you like, of science hiding? Where do we find science? You know, we have the impression that science is living, in some sense, in journals and in the hands of very austere professors wearing thick glasses, wearing white lab coats, in sophisticated institutes and expensive laboratories and so on. And all of these are, of course, true. And there's a lot to be said for that impression. It's all true. But at the same time, this impression leads us to another impression, which is that when those institutional, if you like, practitioners go on holiday, science stops working, no longer exists. But that's not true. Because while we are on holiday, even if we are disgusted with science, nature keeps practicing science. Yeah. It's busily satisfying and executing laws of science 24 hours a day, 7 days a week, in every corner of the universe at all times. So we are brought finally to the question, why toys? There is a passage in a little-known work of Aristotle called De Partibus Animalium, and it concerns Heraclitus. He was a great, famous pre-Socratic natural philosopher, if you like, equivalent of a Harvard professor of the antiquity. And the passage is this, in English translation. In all natural phenomena, there is something of the marvelous. There is a story that some visitors once wished to meet Heraclitus. And when they entered and saw him in the kitchen, warming himself at the stove, they hesitated. But Heraclitus said, "Come in, don't be afraid. There are gods even here. Enaigar kai entautha theus." To my gentle and patient audience, and to the leadership, and especially to the staff of Radcliffe Institute, Thank you.